Today we're going to talk about bonding, so how atoms stick to each other basically, and mainly covalent bonding. So covalent bonds are shared electrons between two nonmetal atoms, so this only has to deal with nonmetals, and they are created by trying to achieve an octet, which is a word that we've talked about in the past. So oct means 8. So every atom is always trying to get 8 electrons around it, so it has a full octet. And every bond consists of 2 total electrons. There's a few things that don't need a full octet, and we'll talk about that in a little bit. So Lewis structures are a way to represent compounds on a piece of paper instead of in 3D. So all of these will be flat structures. And Lewis structures only represent covalently bonded compounds or molecules. There are no metals in Lewis structures ever. So the difference between ionic and covalent things, remember, is ionic compounds always have a metal. That'll be a good review for later on this year as well. So just keep that in mind. If it has a metal in it, you're not going to draw a Lewis structure for it. Lewis structures only show valence electrons. And remember, these are the same as group A numbers on your periodic table. So if you don't have your periodic table out, go ahead and get that out. You're going to want it for the rest of this lesson. It's really important. So you can pause the video here if you need to and get that out. Electrons are grouped in pairs for Lewis structures. And I'll show you what that looks like with some examples. Find lithium on the periodic table and notice that it's in group 1A. And that means that lithium has 1 valence electron. So we're going to represent that electron with a little dot. So just draw a dot right next to lithium. Now find chlorine on the right side of the periodic table. Chlorine's in group 7A. So chlorine's going to have 7 total electrons. And the way I want you to draw them around the atom is first we're going to put 4 electrons down. Make 4 dots. 1, 2, 3, 4. Then they're going to start to pair up. So it's a total of 7. We'll have 5, 6, 7. So you should have 7 around. This one has no pair. It's just an electron by itself. Okay, we'll try one more with oxygen. So oxygen is in group 6A. So he'll have 1, 2, 3, 4, 5, 6 electrons. And you'll notice these two are both unpaired and they want to stay that way. If electrons can be by themselves, they kind of like it better that way, because they're both negative and they want to stay as far apart from each other as possible. So pause the video here and I'd like you to try the rest of the atoms listed on the page. So sulfur, boron, and carbon. Alright, let's see how you did. Sulfur is right below oxygen, so it's going to look identical to oxygen. So if you fill in that structure, you'll notice that. And sulfur has some very similar bonding properties with oxygen. It's going to be it's going to do some things that are in common. Boron just has 3 electrons, so they will not be in pairs. You're just going to put them around boron by themselves. And carbon is the most versatile atom on Earth. It can bond with so many different things because it has 4 electrons. They're all unpaired. It's like having a Lego with 4 little spots where other atoms can come in and stick to carbon. You and I are made completely of compounds that have carbon in them for this reason. Now we're going to talk about the directions for how to draw Lewis structures for molecules. So the very first thing you're going to do is to find the sum of the valence electrons from all the atoms in the compound. So go ahead and look at the examples that are listed below this box. There's a whole bunch of them, and the first thing we're going to do is find all of their valence electrons. The first thing you're going to do is count up the total number of valence electrons. So the first thing is find your first atom. Find your first atom and find out how many valence electrons it has. So carbon has a total of 4, plus You're going to have 4 hydrogens, so it's going to be 4 times the amount of valence electrons hydrogen has, which is 1. And that's going to be a total of 8. You'll notice that it's a multiple of 8, obviously, so that's what we're kind of shooting for here. Then you're going to put carbon in the center because it's listed first. It's also the least electronegative. You're going to put carbon in the center, and then you're going to put the hydrogens around the outside. So typically, the atom that you want in the center is the one that's listed first. Okay, I want you to do the same thing with the rest of these molecules. Find their total number of valence electrons, and then arrange the atoms without any bonds yet. Just arrange the atoms so that all of the atoms are as far apart from each other as they can be around the central atom. Pause the video here. Okay, let's see how you did. Again, carbon has 4. Plus 4 times 7 will be a total of 32, because bromine has 7 valence electrons. So we'll put these all around the outside, as far apart from each other as they can possibly get. Nitrogen has 5 plus 3 times 1. It's a total of 8. Once again, nitrogen will be in the middle, and this time, since you only have 3, you're going to spread those hydrogens as far apart from each other as they can be, and that'll be in the shape of a triangle. So go ahead and do that. Change the shape. If you made it kind of more like a T, you need to make it in a triangle shape like this. Boron has 3 valence electrons, plus fluorine is 3 times 7, so this will be a total of 24, which is also divisible by 8. Put boron in the center and fluorines around the outside. So all of these atoms that are just kind of flailing around out here, they all have to have at least one bond. So draw one straight line between each of the atoms. So draw one straight line between each of the atoms, and that will represent your bond. I don't know if I'm going to be able to do this very well. So each one of these is 2 electrons. And if you count up your bonds here, that's a total of 2, 4, 6, 8. So this one's completely done. Okay, for carbon tetrabromide, we're going to do the same thing. So start with 4 bonds, linking all of the atoms together. So you've used 8 total electrons so far out of the 32. So what we need to do is go back through and add electrons onto all these bromines. So we've counted 2, 4, 6, 8. And we're going to start in pairs around the bromines. 10, 12, 14, 16, and I haven't really left myself enough room here, but we'll try to weasel them in. 18, 20, whoops, 22, 24, 26, 28, 30, 32. So now if you notice, every single atom has 8 electrons around it. Some of them are shared between carbon and bromine, but this one has 2, 4, 6, 8 around it, and the carbon has 2, 4, 6, 8 around it. So usually you're aiming for symmetry because those electrons want to spread out as far apart from each other as they possibly can. Alright, let's do another one. This time we're shooting for 8 total electrons with NH3. This is ammonia. So you'll notice this time it's a little different. You've got only 3 things around the outside. So we're just going to put in 3 bonds. So that's 2, 4, 6. But we're supposed to put 8 electrons in this molecule, so we have 2 extras left over. The hydrogens can only support 2 little electrons. Hydrogens are small and they can only hold 2. So we're going to put those 2 extra electrons on nitrogen. 1, 2. Now I want you to go ahead and label this. We haven't labeled it before, but this is called a lone pair. Sounds like an oxymoron, but it's a pair by itself. Maybe put a little circle around this so you remember. That is a lone pair. And this one has tons of lone pairs on it. Okay, pause the video and see if you can figure out what to do with boron trifluoride. Okay, let's see how you did. This time you have 24 electrons to deal with. So we're always going to first start with simple bonds. 1, 2, 3. So that takes care of 3 total. That takes care of 6 total. And then all of these fluorines, you know how much fluorine loves electrons. It's going to have electrons around it as well. So we'll do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And boron doesn't have an octet. He's only got 6, but that's okay. Boron's okay with that because he's a really, really small atom. I want to draw your attention back to these rules about how to draw Lewis structures for molecules. I went through all of them and the examples, but we didn't go through them step by step. So it's important that you read through them. And look at the exceptions for small atoms down at the bottom. So hydrogen only needs 2 total electrons around it. That means 1 bond. And boron and beryllium can accept less than an octet. So they don't have to have 8 things or 8 electrons around them because they're just too small to even handle that. They can't accept all those electrons. Go ahead and flip over to the back of your paper. Okay, here are a few more examples. We'll start with water, most common substance. So first, find valence electrons. Hydrogen has 1 valence electron, but there are 2 of them. So we'll do 2 times 1 plus 6 for oxygen, and we get 8 total. Now the rule I've told you is that the first atom is usually the central atom. But in this case, hydrogen is just too small to be the central atom, and there's also 2 of them. So in this particular case, we're going to put oxygen in the middle and put 2 hydrogens off to the side and connect them with at least 1 bond. Hydrogen can actually only hold 1 bond, so that'll be it for the hydrogens. So there's 2, 4, but we need a total of 8 electrons. So think about where you might put those extra electrons. They can't go in the hydrogen because they can't accept anymore. Hydrogens will never have lone pairs. So we're going to put the remaining electrons, 2, 4, 6, 8, around this oxygen. So you have a total of 8 around the oxygen. Each hydrogen only has 2, that's all it needs. Okay, let's try carbon dioxide. Carbon has 4, plus there's 2 oxygens, and each one of those has 6. So 2 times 6 is 12, plus 4 is 16 total electrons. For carbon dioxide, you have carbon listed first, so you're going to put carbon in the middle. You're going to put the 2 oxygens off to the side with at least 1 bond. Okay, so you have a total of 16 to deal with here. So think about who likes electrons more, oxygen or carbon. That'll kind of help you deal with this. So this is a strange situation. I want you to actually just put your pencil down for a second and watch me do this. So we're going to give everybody all the lone pairs they could want. So there's 2, 4, 6, 8, 10, 12, 14, 16. You can see we're already starting to run into a problem. 18, 20. This is an issue. We can't have this. Now, everybody has an octet, which is what they want, but we have way too many electrons spread out over here. We can only use 16. So think about what we could do to solve this problem. Instead of having them all spread out like this, we're actually going to have some sharing of electrons going on and some extra bonding, or it's called a double bond. So we're going to take away electrons from both the carbon and one of these oxygens. So take these two away, take these two away, and you're going to make a double bond. That's just another bond that goes right in here, if I can get it to work. Okay, so now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. That's still too many. We're going to do the exact same thing on the other side. So we're going to take another pair of electrons away from carbon and another pair away from oxygen, and we're going to put in a double bond. 2, 4, 6, 8, 10, 12, 14, 16, and hey, what do you know? That's the right amount. One little note I want you to write on here: double bonds are stronger than single bonds. Carbon dioxide is an extremely stable compound for this reason, and that's why we have problems with it as a greenhouse gas, because these bonds are so difficult to break, and they also, this compound stays around the atmosphere for a long time. Let's try something a little more complicated. This is called ethane, and there's 2 carbons and 6 hydrogens. So we're going to follow our same process. 2 times 4. This carbon has 4 valence electrons, plus 6 times 1. So that's 8, plus another 6 is 14. So the structure for this one, it's actually got 2 central atoms. And if you ever take organic chemistry, this is something you'll see a lot. So carbon forms the backbone of most compounds that are used in biology, and you may have even seen some of this last year, although you may not have known what it is yet. So we're going to bond these 2 carbons together with 1 bond, so that's worth 2 electrons. Then I'm just going to sprinkle the hydrogens around the carbons. Remember, hydrogens can only have 1 bond, so you can't stick hydrogens to other hydrogens in a chain. It just won't work. So now we have 2. We're going to put in some more bonds. 4, 6, 8, 10, 12, 14, and that is ethane. I don't really expect you to remember that, but she'll probably see it again in the future. Okay, we have almost the exact same compound here down at the bottom, but instead of having 6 hydrogens, we only have 4. So this time you're going to take 2 times 4 plus 4 times 1. You're going to set it up the exact same way. 2 carbons in the center. Put your hydrogens around. But this time we only have 4, so I'm going to space them out like this to try to get all the hydrogens as far away from each other as we can. So this is going to be a total of 2 times 4 is 8, plus 4 is 12. So 1 bond in the center. So 2, 4, 6, 8, 10. We have 2 more electrons to deal with. And if you notice, these 2 carbons here don't have a full octet. Right now they only have 2, 4, 6, 2, 4, 6 on each side. So we're going to solve that problem by putting a double bond right there. Now he's got a different name. It's called ethene.